Watch a heavy semi-truck tire slam over a wide, dark gap in the middle of a concrete highway. Up close, this harsh separation between road sections looks exactly like catastrophic structural damage. You can find these unnerving, open crevices sitting right in the middle of massive infrastructure projects all over the world. Engineers explicitly design these open crevices to be part of the bridge's working mechanism. These purposeful weak points are integrated into the concrete and steel of our most vital highways every single day. Designing a bridge to be perfectly rigid actually increases the risk of it breaking apart under its own pressure. To understand why the gap has to be there, picture a massive steel bridge absorbing intense, direct sunlight on a hot summer afternoon. That heat triggers thermal expansion. Thermal expansion is the physical tendency of matter to change its shape, area, and volume in response to a change in temperature. At the microscopic level, as temperature rises, metal molecules absorb heat, vibrate intensely, and physically push apart. When ambient temperature drops, the inverse reaction occurs. The molecules lose energy, slow their vibration, and pull tightly back together. A single molecule shifting its position is imperceptible. But apply this physics to thousands of tons of steel stretched across hundreds of meters, and the effect scales up dramatically. The compounding microscopic shifts cause the entire physical footprint of the bridge to grow several centimeters in length by mid-afternoon. Bridges are highly dynamic structures. They are locked in a continuous, invisible cycle of physical transformation, expanding and shrinking day after day. Imagine if engineers built a continuously expanding steel span with zero empty space to grow into. Without room to expand, swelling steel beams violently push against one another, building immense internal stress. With nowhere to safely direct that pressure, rigid structural nodes fracture, sending deep cracks spreading directly into the supporting concrete base. Early structural designs that failed to account for thermal expansion learned this the hard way, resulting in twisted beams and sudden, catastrophic collapses. Trapped internal kinetic energy exerts more destructive force than the weight of traffic or the pressure of a storm. In massive architecture, absolute rigidity forces a structure to fight its own materials until it fails. The calculated engineering solution to release that trapped kinetic energy is the expansion joint. An expansion joint is an assembly designed to hold parts together while safely absorbing temperature-induced expansion and contraction. During the heat of the day, the interlocking teeth slide smoothly together, closing the gap to safely absorb the swelling metal. As the cooling metal shrinks away at night, the interlocking teeth pull apart, opening the gap back up. This quiet, continuous motion is the single most important physical force keeping the entire span safely in the air. When you see a heavy tire roll over that dark separation in the highway, it interacts with a calculated, engineered release valve. Our strongest man-made materials cannot physically overpower the sheer thermodynamic force of the sun. The bridge survives by actively yielding to those elemental forces. It holds itself together by allowing itself to pull apart.